You know, every single time you shop online or send a private message or log into, well, pretty much anything, you're relying on this really revolutionary piece of mathematics that completely changed the digital world. So today, we're going to unlock the secrets behind that very system, the RSA algorithm. And believe it or not, it all starts with a very old classic paradox. Right, think about this. For centuries, this was the ultimate catch-22 of secrets. If you wanted to send a coded message, you first had to get the secret key to the person you're sending it to without anyone else grabbing it along the way. That's a massive security hole. So how in the world did we solve this for the internet, where we need to talk securely with people and servers we've never even met? Well, the solution was absolutely genius. It was to completely rethink what a key even is. The old way, the traditional way you see on the left, used one single key. That key both locked and unlocked the message. But the new way, public key cryptography, splits the key into two separate pieces. And that's the revolutionary part. This shift in logic. Instead of one key that does it all, you have a pair where one key only locks and a totally different key only unlocks. And this two-key system is the incredible answer to that whole key exchange problem. So let's break down exactly how this amazing idea actually works. Okay, so think of the public key like an open padlock. That's the best analogy. You can make millions of copies of this open padlock and just hand them out to everybody, give them away. Anyone who wants to send you a secret message just takes one of your padlocks, puts their message in a box, and snaps it shut. But here's the critical part. They can't reopen it. Once it's locked, it's locked. Only you can open it. And this is why. The private key is the other half of the pair. It's the one unique, one-of-a-kind physical key that you keep totally secret, hidden away. It is the only thing in the entire universe that can open those padlocks that you handed out. This is the core idea, and it's so brilliant. Anybody in the world can lock a message for you, but only you, with your special secret key, can unlock it. Now, this whole concept didn't just appear out of thin air. The idea was first dreamed up by Diffie and Hellman back in 1976, but it was just a concept. It took 2 more years until 1978 for 3 guys, Ron Rivest, Adish Shamir, and Leonard Adleman, or RSA, to create the first practical working algorithm that actually made it all real. And that's the system that pretty much runs our digital world today. So we've got the concept down, right? The public padlock and the private key. But how do you actually create them out of pure mathematics? How do you build this digital lock? Well, let's take a look at the blueprint. This is it. This is the whole ball game. The entire security of this global system comes down to one simple, hard truth. It is incredibly difficult for computers to do multiplication in reverse. You and I can multiply 2 gigantic numbers together in a split second with a calculator, but trying to take that massive result and figure out which 2 original numbers you started with, that is a nearly impossible task. Okay, so the whole process unfolds in 3 pretty clear stages. First, you've got to actually generate that unique public and private key pair. Then, whoever wants to send you a message uses your public key to lock it up. And finally, you use your private key to unlock it. So let's zoom in on that first, most important step, key generation. All right, here's the court recipe. It all starts when you secretly pick 2 massive prime numbers. We'll just call them P and Q. You multiply them together, and you get this even bigger number, N, which you make public. Now here's the magic trick. You use those same secret primes, P and Q, to calculate your secret private key, D. So your public key is made up of that public number, N, and another number, E. But your private key is made up of N and that secret number, D. And the whole thing hinges on this crucial point right here. Even though everyone on the planet can see N, the only way to figure out the private key D is if you know the original secret prime numbers, P and Q. And to really get a sense of how difficult this is, just imagine this. Imagine N is the exact total number of grains of sand on a huge, vast beach. You know that total number. But trying to find the 2 specific original grains of sand, the 2 prime numbers that were multiplied together to get that total, that is the monumental, mind-boggling task that faces anyone trying to break RSA. But, just because something is really, really hard doesn't mean people aren't going to try to break it. The history of RSA is also the history of all these clever attempts to crack it. It's this constant cat-and-mouse game between the code makers and the code breakers. The most obvious attack is just trying to factor that giant number N to find those 2 grains of sand. But there are more clever, more subtle ways in. Attackers can look for mathematical weaknesses, like if the public exponent E is too small. And what's really shocking is that some of these attacks don't even need the whole key to work. And that brings us to that partial key exposure attack. The math behind this is pretty intense, but the takeaway is just, wow. It has actually been proven that if your private key D happens to be smaller than this very specific value, or, get this, if an attacker can learn just 1/4 of the bits of your private key, they can often reconstruct the entire thing. It just goes to show you there is almost no room for error. So, you might be thinking, with all these different attacks, why on earth are we still using an algorithm from 1978 to protect our most important data? How has it possibly survived all this time? Well, here's the secret. We don't use that basic textbook version of RSA anymore. Modern systems use a critical upgrade called OAEP. In simple terms, before your message gets encrypted, OAEP pads it out with a bunch of random data. This process basically smooths over and eliminates many of those subtle mathematical weaknesses that attackers were trying to exploit. It turns old-school RSA into a hardened system that's ready for modern attacks. And its legacy today. I mean, it is absolutely everywhere. It's not just about keeping messages secret. RSA is what makes digital signatures possible, proving a document is real and hasn't been tampered with. It's the reason for that little padlock icon in your browser that lets you shop online securely. Honestly, its very existence has pushed the entire field of cryptography forward for decades. So, what's the big takeaway from all this? The incredible, lasting strength of RSA isn't just about it being complex. It's actually about its simplicity. It's built on a single, timeless mathematical truth that some problems are just fundamentally incredibly hard to solve. And it's that elegant difficulty that continues to serve as the digital locksmith for our entire modern world.